let's put together a couple of examples here that will kind of bring a lot of different ideas together, including Lewis diagrams, um, electronic configurations, orbital filling diagrams, and we can see how they complement one another. All right, so here we go. Using Lewis diagrams and orbital filling diagrams, give examples that show how sulfur can have valences of 2 negative, 4 plus, and 6 plus. All right, so let's start with the Lewis diagram, and we're going to start with sulfur. And sulfur we know is in group 6, so we're going to give that 6 valence electrons. And we're going to add in our hydrogens. We're going to match up the unpaired electrons like that and connect the dots. And we've got H2S. Now, taking sulfur as the central atom here, this is going to be the 3s and 3p orbital filling diagram. So just orbital filling diagrams only use valence electrons. So sulfur is, of course, would be 3s2 and 3p4 would be the valence electrons on sulfur. Okay, and we can see here, we can actually complete this octet by throwing in a couple of hydrogens there. And you can see that we've got a nice octet right over there. Furthermore, yeah, we can see the bonds right over here. This bond would be right here, and this bond would be this one right here. And this electron pair right over here, and these electron pair here would be right over here. So you can see we've got electron pair here, electron pair here. That's our bonded pair, and that's our bonded pair as well. Okay, so that one works out really nice. So our Lewis diagram, which is right here, complements our orbital filling diagram. All right, let's go to the next one. So the examples I used here for the 4 plus is SO2 and sulfite, SO3 2 negative. So these Lewis diagrams will get a little bit trickier, and we're going to start to extend beyond the octet rule as well. So let's start with SO2. So again, we're going to start with central atom sulfur. By the way, sulfur and oxygen have equal number of valence electrons. Whenever that's the case, and what's usually the case is the least electronegative is going to go to the center. The most electronegative is going to go to the outside. All right, so there's my sulfur. And I'm going to draw concurrently here the orbital filling diagram. So we've got our 3s and 3p, just like the last example there. All right, so there's my 3s, there's my 3px, my 3py, and my 3pz are going to be over here. So there's my z, there's my y, there's my x, and there's my 3s. All right, so that all kind of makes sense from the number of electrons and the kind of the distribution. Okay, well, we're going to need a couple of oxygens here. So I'm going to throw in a red oxygen, and so here's my first oxygen, and you can see that this is going to match up really nicely. And that would make SO, but you can see now I'm stuck, all right? Like we had those bonding electrons here. So I've put in oxygen like right here, that double bonded oxygen, but now I'm stuck. I have nowhere left to bond. But SO2 exists. It just does, all right? Well, like whether we like it or not, SO2 exists. So we've got to have our theory match what we have in the real world, the SO2 molecule, which we know exists. It's a big gas in acid rain, and it's a fairly potent pollutant in the atmosphere. So the theory is going to go along something like this. Well, we have to put another oxygen, but we've got non-bonding electrons and non-bonding electrons. So this is what we're going to do. I'm going to take this and we're going to erase this, and we're going to separate these and put them into different orbitals. What does this look like on the orbital filling diagram? I'm going to get rid of that 3p, and I'm going to move it into the 3d orbital. I'm going to pop that electron right here. So I've just separated it. So I've separated it here, all right, with the two electron pairs, and I've separated it here on my orbital filling diagram. All right. Now, again, you're probably thinking, why would sulfur put an electron into a higher energy level? Didn't sulfur become less stable? And the answer is yes, but oxygen is becoming more stable, and the overall picture is becoming more stable. So we're going to add in our other oxygen like this. So there's our oxygen. And so we can put in another double bond. Whoops. Let me undo that. And I'm going to put in my that one bond and that second bond. So that is what my orbital filling diagram is now going to look like. I've got a double bond here, a double bond here, not quite the same order that we put them in. And we have an electron pair right here, which is this electron pair right over here, right? So that's how we just constructed that, and it makes sense from that theory point of view and from the practical point of view that SO2 exists. Okay, sulfite. Here we go. So sulfur is in group 6. And yeah, let's get rid of the orbital filling diagram for SO2. And we are going to use an expanded octet again here. All right, so there's our sulfur. And we're going to have to put 3 oxygens on this and a 2 negative charge. So I'm going to put an oxygen here. And it's in group 6. So 1 here, 2, 3, 4, 5, 6. And another oxygen here. 1 here, 2, 3, 4, 5, 6. These are now neutral, but they're not stable. You can see they don't have an octet. So we're going to have to add an electron here. I'll put a little purple X here just to show that it's a little bit different. Going to gain 1 electron from some external source, like a wandering sodium or something like that. We'll check those formal charges at the end. All right, I would assume they're going to be negative, but let's put this through a bit more of a rigorous test at the end. Okay, yeah, so we've got a single bond oxygen and a single bond oxygen so far on our Lewis diagram, or on our orbital filling diagram. So now we're stuck, but we haven't accounted for the sulfite ion. So we're going to do the same thing again. We're going to move this electron pair to the first excited state. All right, and let's take this electron, and we're going to move it into the 3D. All right, so we're using that expanded octet, and we can pop in another oxygen here. And make our double bond. Okay, and that double bond, of course, would be here and here. Those 2, 1, 2. Those are the 2 bonds that we would make. Okay, formal charge. Actually, let's do it on all the diagrams here. I didn't do it on the SO2, but formal charge on the sulfur would be group 6 minus 2 dots minus 4 bonds is equal to 0. And the formal charge on this one of these 2 oxygens, they're identical. Group 6 minus 4 bonds minus 2 electrons is equal to 0. This is neutral. All right, so that's a neutral molecule. Um, yeah, so then let's go to we'll start with the sulfur again. Formal charge is going to be equal to group 6 minus 2 dots minus 4 bonds is equal to 0. And this oxygen on the left, the red oxygen, is going to be group 6 minus 4 dots minus 2 bonds is equal to 0. Now let's look at these two other oxygens here. All right, so these two other oxygens are going to be, this is going to be group 6 minus 6 dots. That funny one with the X is that one that it drew in to create the octet. And minus 1 bond is equal to -1. So that will have a -1 formal charge. And so will this one here. Now, that's how I always do them. I prefer them. Oftentimes you'll see in textbooks, they will pretty much do this. So they'll do sulfur, double bond, oxygen, single bond, oxygen, single bond, oxygen. Notice that oxygen, of course, is in period 2, so it has to have an octet. And sulfur doesn't have to, though. It doesn't have to have an octet. Why? It's in period 3. It has d orbitals. All right. Oxygen doesn't have d orbitals, so it can't expand the octet on oxygen. It's only got 2s and 2p. That's it. Right. So they can't have more. Sulfur can, though. So yeah. So this is a bit of a wimpier diagram right over here. I don't like it as much, but you see it all the time in textbooks. I like the slightly more rigorous, this version right over here, just because you locate exactly where that formal charge is. So 0 on the oxygen, 0 on the sulfur, -1 on the oxygen, -1 on the second oxygen. All right. So then we form that SO3 2 negative. And we basically followed 2 rules, right? Period 2 has to have an octet, like oxygen and nitrogen and carbon. They have to have octets. But period 3 and beyond don't have to have octets, right? But the formal charge has got to work out, of course, in order for it to be a correct diagram. Okay, last one. SF6 and sulfuric acid. And let's go again here. 3S, 3P, 3D. So let's go with SF6. So we'll put sulfur in the middle. Group 6. And we'll put fluorine around the outside. So we've got 1 fluorine atom here and another fluorine atom here. And SF2 is stable. And let's draw that one kind of where we are right now. This is not the final diagram, but you can see it's got 2 empty spots, and we put 2 fluorines in there. All right, but we're not done because we've got to get 6 fluorines. We've got 2, so we've got 4 more to go. We have no bonding spots right now, but what we're going to do is we're going to go to the second excited state. We're going to move this electron here and this electron here in the 3s. And we're going to move them both into the 3D. This guy as well. So we're going to put the second excited state of sulfur. So this is sulfur, and we saw in the previous example in that 4+, it was in the first excited state. Now we're in the second excited state because we're going to move 2 electrons. Right? The 2 electrons are going to move into that 3D orbital. Again, yes, is sulfur more unstable? Yes, it is. But the fluorine, you know from the previous unit, fluorine loves to grab electrons. Why does it love to grab electrons? Because it becomes more stable. As it becomes more stable, that overall picture becomes more stable. Okay, so let's draw this diagram. So I'm going to just separate these guys. I'm going to put them into different orbitals here. And there we go. Let's put one here and one here. And we're going to have a fluorine 1, 2, 3, and 4, for a total of 6. There's our SF6. All right, and of course we're in the second excited state, and we can match up all those 6 sulfurs with 6 single bonds right over there. All right, same thing again. We'll do this with sulfuric acid, another 6 plus example. And we'll go right back here to, sorry, I did that incorrect. Let's erase that. Here's our 3S, 3P, and 3D, which we're eventually going to use. So let's start with the sulfate. And again, we're going to start off with sulfur, group 6. And we've got to get 4 oxygens around there. And then we're going to add the hydrogens add on to the oxygen, because they're going to form that, they're going to get the electrons pulled away by the very electronegative oxygen. So let's put the oxygens over here. We've got 1, 2, 3, 4. Now, here you can see, so oxygens in group 6. I'm going to draw 6 dots around all of them. All right, so that's where they all are. And like right now, we can make 2 single bonds over here. So a single bond here and a single bond here. Now those again are neutral but not stable. And we have to add some electrons here to complete that octet. Oxygens in period 2 needs an octet. Now these ones here, you'd see, well, you're saying, well, they're not going to bond. Well, of course not. We're going to have to move these guys into a higher energy orbital. So let's do that. Let's move this guy and move this guy here. There we go. And we'll match those guys all up now. And we can do a formal charge here. Sulfur is in group 6, 0 dots minus 6 bonds. Oxygen, so these 2 oxygens right over here would be a formal charge of 6 minus 4 dots minus 2 bonds. Now we're going to get some -1 charges here. This is going to be a -1 charge. This is going to be a -1 charge. And just to prove that, this is going to be group 6 minus 6 dots minus 1 bond is equal to -1. So that's how that sulfate would look. All right, so there, I'll neaten this guy up. And also an acceptable diagram, but just not as rigorous, I suppose, with the charge. A lot of textbooks will just throw that -2 on the outside, right? And I would just more specifically locate them on each of the 2 oxygens. All right, so that's a lot, but that shows a lot of kind of good examples of how, these actually work, right? So the bonds that you see in the orbital filling diagram match what you see on the Lewis diagram. All right, so yeah, I hope that works out for you.